Welcome to Excel 2013 Statistical Analysis video number 68. Hey, if you want to download this workbook file to follow along or the PDF file, click on the link below the video. Hey, in this video we want to talk about population difference, just like we've been doing for the last few videos in Chapter 10. But now we want to talk about matched samples. And we're going to look at inference, both hypothesis testing and confidence interval. Now, the nice thing about matched samples is that the calculations are a lot different than when we had two independent samples in our last couple videos. Now, what is a matched sample? Each sample element provides a pair of data values. So for example, if one worker tries two different production methods and provides two different times to complete the production, and this is the example we'll do in this video, that means we have matched samples. One person is doing two different things. Now, because they're the same person for each data value, the variation and sampling error between the two values is reduced. Think about this, and I know this is kind of written sideways off the side, but think about this. If you have two different workers, those workers may have different abilities, and that may lead to some of the sampling error. But when you have the same person, that means one worker doing two different methods, you know, their strength, their ability, their knowledge is the same for both values. Other examples of matched samples. One person gives a rating for a product, 0 to 10, before watching an ad, and then gives the same rating after watching the ad. The rating would be like how much they want to buy this product. That's one of your homework problems. Another example, you could have two different but similar workers provide times for production methods 1 and production method 2. Here you'd have to try your best to get similar workers in age and experience and strength, etc., for the two values. Now, the nice thing about this is number 2 here, the pair of matched sample values are then subtracted to get the difference. And guess what? Then we only have one column to make our calculations on, and we're back to Chapter 3 where we did averages and standard deviations based on one sample. In essence, the difference will be our sample. Now, I'm going to hit page down and go to the next page. Now, we want to compare and contrast matched or paired samples and independent samples. So independent sample design. Samples select from two populations in a way that the elements making up one sample are chosen independently of the elements making up the other samples. Hey, in our last video, we had miles per gallon for imported car and domestic. Those were independent samples, not related in any way. A matched sample design, one simple random sample of elements is selected, meaning we select the workers, and two data values are obtained for each element. As we mentioned just a second ago, this one's written more neatly than on that other page. Matched sample design often leads to smaller sampling error than the independent design because variation between sampled items, like difference in production workers, is significantly reduced as a source of sampling error. So if you can, right, if you have two production methods, instead of doing two random samples, if you can get the same person to do it, it's going to make everything much easier. Now I'm going to page down and go to the next page. Here's the example we're going to do. And the key for matched samples, the key to the analysis of matched sample design is we consider only the columns of difference. And we'll see, oh, right here, here's the column of differences. So we'll just have one column that we calculate the mean and standard deviation from. Our example of matched samples, we're going to have an established method for making the quad boomerangs. So this is a production method, right? So sample 1 will be method 1. The new method for making quad boomerangs, that'll be considered sample 2. That'll be method 2. We do a simple random sample to pick 10 employees to try both methods. So our workers 1 to 10, we sampled from the whole big pool of workers. Then each one of the 10 workers uses method 1 and we time it. Then they do method 2 and we time it. And we calculate the difference. Now if I go to the next page down, here's our formulas. The mean of matched sample differences, it's going to be represented by D bar, right, for differences. Hey, it's just the sum of d sub I divided by n. Now, d sub I right here, that's the particular difference. If we have 10 workers, right, we'll have 10 differences. Notice that d bar is the mean of the matched sample differences. So up here, we're just going to calculate the mean of all the differences. Add up all the differences and divide by the count. Standard deviation for the differences, it's exactly like we did back in Chapter 3. We just take d sub I, that's the particular difference, minus the mean. That gives us the deviation, right? And back in Chapter 3, we knew that we can't just add them all up because it'll get 0, so we squared them. And then divide by n minus 1 and take the square root to undo that square there. That gives us the sample standard deviation of our differences. Then our test statistic, just as we did all the way back in Chapter 3, the first time we calculated a z. Here we're going to use t distribution and the differences. We take the mean minus the difference for the population, and we'll assume that it's 0 because we'll be testing to see whether it's different. The mean minus the 0, so that'll just be the mean. And we divide by our standard error. Standard deviation for the differences divided by the square root of n. Now, 1, 2, 3, there's our base formulas. I know this is kind of crooked up here, but our confidence interval is simply going to be, oh yeah, the actual mean of the difference plus or minus some margin of error. And remember, margin of error is based on number of standard deviations. We're using t, so that t sub alpha divided by 2 means t upper, times our standard error. Our standard deviation times our number of standard deviations will give us our margin of error. Now, in just like last video, we will have a built-in feature from the Excel Data ribbon tab, Data Analysis. It'll be called T.DIST, Pair to Sample Means. And finally, the rules for building our confidence interval and hypothesis testing are exactly the same as earlier in the class. Now, if you page down, I have handwritten notes for our example that we're going to do. 1, 2, just 2 pages there. All right, now we're going to jump over to Excel. All right, now over in Excel, we have our 10 workers and our times for method 1, times for method 2, and these are in minutes. So now we calculate our column of differences. Equals, and we got to get this right, 1 minus 2. Control, Enter, and double click and send it down. So that means 1 minus 2, it took 1 minute longer for the first one. This one is minus 0.3 minutes. The first one was 0.3 minutes faster. Now, our question is at alpha of 0.05, is there a difference in method 1 and method 2 for making quads? And so we always set up our alternative hypothesis first. So H sub A for hypothesis alternative colon, and then mu sub D. We're going to assume that the mu sub D, mean of the differences, is 0. So just as we've done before, both null and alternative will be compared to the mean of the differences in the population. So I'm going to say equals, click on that 0 F4 to lock it, and Control Enter to populate that formula down. Now we can work on the alternative, right? Is there a difference? So that means not equal to. So space, and then as we've done earlier in the class, we're going to use the not, less than, greater than symbol in Excel. That means not. So that means if this is not, this one is equal. A space and then an equal sign. So our null hypothesis will be that the difference is equal to 0. The alternative will be that it's not equal to 0. Now we can set up our alpha, 0.05, and Enter. Remember, alpha is the risk that we reject the null hypothesis even when it was true. Alpha divided by 2, we're doing a two-tail test, so we have to divide it by 2. There'll be 0.025 in either one of the tails. Now, if we were to draw a picture, that picture is over here in the PDF, it would look like this. Notice there's the 0, mu sub D. We'll have to calculate our critical values, beyond which, boom, that direction or this direction, we will reject the null and accept the alternative. Any test statistic that falls in here will fail to reject the null hypothesis. All right. So let's back over to Excel. Now the calculations, and you can see they're right here, they're just straightforward. The mean of match sample differences equals, hey, I'm calculating it with the average on a single column. And enter. So our mean difference is 0.53 positive. So that means our point estimate for the difference is that there was about a half a minute longer for method 1. Or said a different way, about a half a minute faster for method 2. Now, standard deviation of the matched samples, hey, equals ST.DIST, and we're using the S. We simply highlight the single column. I love this match sample because it makes our calculations quite a bit easier. Now, the sample size, we're counting numbers, so I'm using count and enter. We're going to need our n minus 1, so equals the 10 minus 1. And that will be our degrees of freedom because we do not know the standard deviation from the population. This is a t-test. Now our standard error, now we don't have a formula over here, but we know it's just standard deviation of the difference is that little thing right there divided by the square root of n. That is not written very nicely, but let's do it here nonetheless. Equals our standard deviation from our sample differences. We'd calculate it from that column, divided by the square root of n. Close parentheses and enter. So our standard error will be 0.2547. Now we can calculate our test statistic. Now the formula here is simply the mean minus our population difference of 0 divided by the standard error. So I'm simply going to go equals open parentheses. There's our mean of the difference minus our mean of difference in the population, close parentheses, and divide by our standard error. Enter. So our test statistic is 2.08. Now we've got to calculate our critical value. Remember, we have two ways to do it, critical value or p-value. If this value right here is past our critical value on either side, then we reject the null and accept the alternative. Otherwise, we fail to reject the null hypothesis. Hey, we're doing t, and as we've mentioned so many times, the T.DISTs are for probability. The T.INVs are for the actual value, in our case a t, a number of standard deviations. Probability, well, we need to go all the way up to 0.025 on the upper end. So I have to say 1 minus 0.025. That's 97.5% probability, comma, and our degrees of freedom. Remember, degrees of freedom tells us which one of the many t distributions to go look at. And when I hit enter, so the hurdle is 2.26. And our test statistics did not make it past that. So we would fail to reject the null hypothesis. Now, I did it this way. And I really like this way because it's kind of our consistent. We've used the inverse and the DIST functions throughout this whole class. But we could get fancy and use the equals t dot inverse. And there's a two tail. The probability, we actually give it the whole probability alpha. And the reason why is because this function knows it's a two-tail. So internally, it divides by 2, comma, and then the degrees of freedom, we calculated it right there. So it is a little bit easier. But in some ways, we've been using the other method so often that in some ways that one seems easier. But there it is. It'll give you the exact same thing. So, I mean, obviously, if you want to double check, I love having multiple ways to do it. Now, we've already, from our critical value and our test statistic, we know what our conclusion is. But let's calculate the probability of getting this value or more on either side, both the upper side and the lower side. So p-value is the probability, so it's equals t.DIST. Now, what are we going to do here? This we want to give it this value right here. Remember, these functions always go from negative infinity up to that particular x, comma, the degrees of freedom is 9, and comma, cumulative. We want it to go from negative infinity up to our test statistic, so I put a 1 for true. Now remember, this will give me all the probability up to that point. I really want the amount on the upper end, so I say 1 minus. Now remember, this is a two-tail. So in fact, we have to double that. F2, and this is where it gets kind of tricky. This is the method we've been consistently using. So we are going to do it. Close parentheses. That makes the minus happen before the times 2. And that's our p-value that we compare to our original total 0.05. Now, in this case, this formula really is kind of complicated. The equals T.DIST two-tail is really quite a bit easier here. We give it the x, that's our test statistics, and the degrees of freedom 9. And it does the rest because it's programmed as a two-tail. Control-Enter. It gives us our p-value that we can compare. That's the probability of getting 2.08 or greater, or minus 2.08 or less. So our conclusion, the statistical evidence does not support the conclusion that there is a difference between the two methods for making the quad boomerangs. The test statistic is not past our critical value, and the p-value was bigger than our alpha, so we fail to reject the null hypothesis. Now, for matched samples, there we go. There's our hypothesis testing. It's just a few other steps because we've already made a bunch of calculations to calculate the confidence interval. This will tell you we're 95% sure that the population difference is between an upper and a lower value. Margin of error. Well, guess what? Margin of error is number of standard deviations times standard deviation. So equals, and for our margin of error, we've already calculated the critical value, which is 2.26. That tells us how many standard deviations times our standard error, which is our standard deviation. And there is our margin of error. We add or subtract to that amount right there. So about 0.5763 minutes we have to add and subtract from our mean of the matched sample differences. Now, we can actually start using the confidence.T function to calculate margin of error. We couldn't use that with our independent samples, but here we have one column we're dealing with. So guess what? Equals confidence. And there's the norm, that's z distribution, and the t, that's the t distribution. And remember, we studied these earlier in the class. This is programmed to do all of the heavy lifting. So when it says alpha, it wants the entire 5%. It knows for a confidence interval that it has to divide it in 2. It also wants the original standard deviation, and it wants the original size. See, it can calculate standard error from that, and it knows to calculate degrees of freedom, which is -1 from our sample size. Close parentheses and enter. So we get exactly the same thing. Now we can simply, for the upper, say equals our mean of the matched sample differences plus our margin of error. Enter. There's the upper end. Equals mean of matched sample difference minus our margin of error. And so there is our range. We are 95% sure that the population difference will be between 1.1 minute and minus 0.0463 minutes. And you remember we mentioned this a couple times. If 0 is contained in our interval, we would come to the same hypothesis conclusion that we fail to reject the null hypothesis, which means there's not enough statistical evidence to support the conclusion that there's an actual difference between the methods. Now, we've done all of this with formulas, which is awesome when you're learning because we have to do all the individual calculations, and it helps us understand the process better. And formulas are awesome because if this data were to change, then these would automatically update. But if we're going to do this just one time, and we don't mind static answers, which means if we change the source data, static means it will not update, we can just use the feature on the data, ribbon tab, analysis group, data analysis. And right down at the bottom, t-test paired to sample for means. Now notice they use paired, we use matched. Well, when I click OK, the dialog box comes up, variable range 1. I'm definitely going to highlight the header and all of the numbers. Variable range 2. Our hypothesized difference, there's no way to link this. There's no collapse button, so we simply have to type the 0 in. We definitely have labels, alpha 0.05, and we want to put it on this worksheet. There's a collapse button there, so we can simply come over, and I'm going to put it like an A15. when I click OK. You got to be kidding me. Look at that. It actually calculated the mean and the variance of each and the count of each, which we did not do. And down here, if we expand just a little bit, there's our test statistic right there. There's our p-value, and there was our critical value. So pretty amazing, nice, quick, easy way to calculate the important numbers for matched or pair samples. All right, so in this video, we did matched or pair samples, where the key concept that determined that they were matched or paired is that these 2 times for the different methods came from the same person. This method is nice because it reduces sample error, and the calculations are a lot easier to do. All right, next video, our last video for Chapter 10, we'll talk about what you do if you're comparing more than 2 means, and we'll learn about ANOVA. All right, we'll see you next video.